Similar to our Sun, other stars in the universe are also powered by nuclear fusion. In these stars, various elements undergo fusion, producing different kinds of energy and elements. Projects like ITER, International Thermonuclear Experimental Reactor, aim to harness nuclear fusion for practical energy production. These reactors use powerful magnetic fields to contain and control the high-temperature plasma needed for fusion. Imagine two magnets with opposite poles facing each other, representing hydrogen nuclei. When they get close enough, they snap together with force, fusion, releasing a spark of energy. The difficulty is getting them close enough to overcome their natural repulsion, similar to the energy barrier in fusion. Unlike nuclear fission, which splits heavy atoms into lighter ones, fusion combines light atoms to form heavier ones, releasing more energy and producing less radioactive waste. Achieving fusion on Earth requires temperatures of millions of degrees and significant pressure, similar to the conditions found in the cores of stars. Successful fusion reactors could provide a nearly unlimited source of clean energy, with the main fuel, hydrogen, being abundant and the process producing minimal environmental impact. Nuclear fusion is a process where two light atomic nuclei combine to form a heavier nucleus, releasing energy. This is the same type of reaction that fuels the Sun and provides the light and warmth that sustain life on Earth. In terms of energy production, fusion is the opposite of fission, which powers traditional nuclear reactors by splitting atoms apart. Fusion produces no greenhouse gas emissions, generates minimal radioactive waste compared to fission, and uses water as its primary fuel source. The challenge lies in achieving and controlling the fusion reaction under Earth-bound conditions. Fusion requires extremely high temperatures and pressures to force nuclei together, conditions that are difficult to create and maintain. By understanding nuclear fusion, we gain insight into a potent potential energy source and the intricate dance of particles that power the universe. To grasp the concept of nuclear fusion, imagine two ice dancers spinning towards each other on an ice rink. As they come close, they must overcome the mutual push of their outstretched hands to perform a spectacular spin together. The challenge in fusion research is akin to forcing these dancers to come close enough, despite their initial resistance. At the heart of fusion physics is the overcoming of the Coulomb barrier, the force that repels charged particles like protons from each other. To achieve fusion, the conditions must be extreme enough to push these particles within a hair's breadth of each other, allowing the strong nuclear force to take over and bind them together. This is achieved at temperatures of millions of degrees, where matter exists in a plasma state, a hot, charged gas where electrons are stripped from their nuclei. Creating and containing this plasma is a monumental task. The Sun, a colossal fusion reactor in the sky, is the most familiar example of fusion power. Every second, about 600 million tons of hydrogen are converted into helium in the Sun's core, releasing vast quantities of energy. This process is natural and has been occurring for billions of years, providing a stable energy output that fuels life on Earth. Understanding solar fusion helps scientists on Earth design better fusion reactors. The Sun operates under a set of conditions that are difficult to replicate artificially. Its immense gravitational pressure allows fusion to occur at lower temperatures than those required in man-made reactors. Here on Earth, we must achieve much higher temperatures to facilitate fusion, necessitating advanced materials and innovative engineering solutions. By studying the Sun, we unravel the secrets of controlling fusion power, inching closer to replicating this source of boundless energy in a sustainable, controlled setting. The quest to harness nuclear fusion began in earnest in the mid-20th century, during a time of rapid scientific advancement. The concept of controlled nuclear fusion first emerged in the 1950s, with various experiments aiming to achieve fusion conditions on Earth. In the 1970s, the development of Tokamak reactors, a Soviet innovation, provided a more stable method of achieving the high temperatures and pressures needed for fusion. The Tokamak's toroidal or donut-shaped chamber design was crucial in containing the hot plasma with magnetic fields. This design is still at the heart of many modern fusion experiments, including the international ITER project, which aims to be the first to produce net energy gain from fusion. The 1990s and early 2000s saw advancements in laser-based fusion, particularly with the establishment of facilities like the National Ignition Facility in the United States. Each of these milestones has contributed layers of understanding, bringing us closer to a viable fusion energy solution. Today, the timeline of fusion research reflects a saga of human ingenuity and persistence. The field of nuclear fusion is currently experiencing a renaissance, driven by both technological advances and a renewed urgency due to climate change. Cutting-edge research facilities around the globe are making strides in overcoming the formidable barriers to sustainable fusion energy. One of the most prominent of these is the international ITER project, which aims to demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy. In parallel, several private companies have entered the fusion arena, propelled by advancements in supercomputing, materials, science, and precision engineering. These companies are exploring innovative approaches to fusion, including new designs for magnetic confinement and novel methods of plasma stabilization. Technological innovations have also enabled better diagnostics and control systems, crucial for managing the behavior of plasma in fusion reactors. Advanced materials capable of withstanding extreme temperatures and radiation are being developed, pushing the boundaries of what's possible within reactor cores. As we continue to advance technologically, the synergy between different disciplines plays a crucial role in moving fusion from theoretical possibility to practical reality. ITER, which stands for International Thermonuclear Experimental Reactor, is perhaps the most ambitious fusion project to date. Located in southern France, ITER is a colossal undertaking involving 35 countries, including the United States, Russia, China, and members of the European Union. Its goal is to build the largest tokamak ever, and to achieve the long-sought-after goal of net energy gain, where the energy produced by fusion exceeds the energy used to initiate and sustain the reaction. The project exemplifies international cooperation in science and technology. By pooling resources and expertise, ITER hopes to address the technical and financial challenges that no single country could tackle alone. ITER's design is based on decades of tokamak research. It aims to contain a plasma 10 times hotter than the core of the Sun within its magnetic fields. If successful, ITER will pave the way for commercial fusion reactors and could fundamentally change the way we produce and consume energy. Supercomputers play a pivotal role in the field of nuclear fusion, where the complexity and scale of the problems require vast computational resources. These powerful machines are used to simulate plasma behavior, test reactor designs, and predict the outcomes of experiments before actual physical trials begin. This computational approach saves time and resources and reduces the trial-and-error nature of physical experimentation. Supercomputing allows researchers to model the intricate dynamics of plasma under different conditions, helping to solve some of the most persistent challenges in fusion research, such as plasma stability and energy confinement. The simulations provide valuable insights that inform the design and operation of fusion reactors. For instance, They can predict how plasma might react to changes in magnetic field configurations or to different materials used in the reactor walls. The development of quantum computing promises to further revolutionize this field. As computational power continues to grow, its integration into fusion research becomes increasingly critical. One of the most compelling aspects of nuclear fusion is its environmental promise. Unlike fossil fuels, fusion offers a means to generate large amounts of energy with little to no greenhouse gas emissions. This characteristic positions fusion as a key player in future strategies to mitigate climate change. Moreover, unlike nuclear fission, fusion does not produce long-lived radioactive waste, reducing the environmental and safety hazards associated with nuclear power. The primary byproduct of a fusion reaction is helium, an inert gas that poses no threat to the environment. Additionally, the fuel used in fusion reactions, such as deuterium and tritium, is derived from water and lithium, resources that are abundant and widely available. Fusion reactors are inherently safe because the fusion reaction is not self-sustaining. It requires continuous input of energy. By contributing to a cleaner, safer energy landscape, fusion technology not only addresses the technical aspects of energy production, but also aligns with broader environmental and ethical considerations. The ongoing global energy crisis, characterized by rising demand, dwindling fossil fuel reserves, and urgent environmental concerns, calls for a radical rethinking of how we produce and consume energy. Fusion energy, with its promise of plentiful, clean power, stands out as a particularly transformative solution. Its development could significantly alleviate energy shortages and reduce reliance on unsustainable energy sources. In regions with limited access to traditional power grids, fusion could provide a consistent, reliable energy supply without the infrastructure demands of conventional power plants. This could foster economic development and improve living conditions in underdeveloped areas. Additionally, fusion energy could power desalination plants and other critical infrastructure, providing clean water in arid regions and supporting sustainable agriculture. The potential of fusion energy extends beyond terrestrial applications. As global energy needs continue to grow, the successful development of fusion energy could play a crucial role in ensuring a stable, sustainable energy future. Despite its tremendous potential, nuclear fusion faces significant challenges that must be overcome before it can become a practical energy source. One of the primary obstacles is the sheer scale of technological innovation required to achieve and maintain the conditions necessary for fusion. The temperatures and pressures needed to sustain fusion reactions are extreme, requiring advanced materials that can withstand intense heat and radiation without degrading. Economic factors also play a critical role. The initial investment for fusion research and reactor development is substantial, and the transition from experimental to commercial reactors involves significant financial risks. Furthermore, the complexity of fusion technology makes it a long-term investment, which can be a deterrent for private sector involvement without significant government or international support. Public perception and regulatory challenges also influence the development of fusion energy. Addressing these challenges requires not only scientific and technological advancements, but also a coordinated approach involving policymakers, researchers, and the public. The journey towards harnessing nuclear fusion is a testament to human curiosity and ingenuity. While the path is fraught with technical, financial, and regulatory challenges, the potential benefits of fusion energy, environmental sustainability, safety, and abundance make it a pursuit worth continuing. As research progresses and brings us closer to a viable fusion technology, the dream of a clean, unlimited energy source becomes increasingly tangible. Looking ahead, the continued support for fusion research is crucial. Public and private investments in fusion technology need to be sustained and even increased to achieve the necessary breakthroughs. Educational initiatives that promote a better understanding of fusion energy and its benefits can help garner public support and mitigate misconceptions about nuclear science. The future of fusion energy is not just about scientific and technological achievements. It is also about shaping a sustainable energy policy that considers the long-term health of our planet. By continuing to support and invest in fusion research, we are not only unlocking the secrets of the stars, but also securing a brighter, cleaner future for generations to come.